So all the vector stuff we've been doing is first going to be used for projectiles. So if I throw a ball across the room, you know it goes both south towards the back of the room and it goes up and then down. That's two-dimensional. We are going to talk today only about launching horizontally. So if we throw it straight out, it is going to arc down. And we'll talk more about this picture in a second. So if it is thrown horizontally, it's going to keep going horizontally. That's Newton's first law, inertia. An object in motion stays in motion. Yes, gravity's acting on it, but gravity acts vertically. Gravity does not pull sideways. Gravity does not make it speed up. Gravity does not make it slow down horizontally. So this means we have constant velocity. Vertically, gravity causes acceleration. You know this already. That's why we did free fall problems in the last unit. Gravity causes acceleration the same way that it did, but only vertically. It doesn't do anything to horizontal motion. We did a demonstration last year about dropping a ball and throwing one horizontally, and they hit the ground at the same time. That is evidence that this horizontal motion does not interfere with the acceleration due to gravity. Same height, but moving versus not moving horizontally. They hit the ground at the same time. So this graphic is one I used to use in pre-AP physics years ago. And this says if I throw this ball horizontally, these ghost balls are what would happen if there was no gravity. The first law of motion, inertia, says it's going to keep moving at a steady rate. Notice they're equally spaced. This set of ghost balls is, well, what if I drop the ball? It's going to move a little bit, and then farther, and then farther and farther. These are scaled so that they're equivalent seconds. So in 1 second it's moved over this far and dropped just a little. Then it's moved far over the same distance horizontally, but dropped farther vertically. Same distance horizontally, farther vertically. Same distance horizontally, farther vertically. So together, these trace out this path. I'll remind you, this is called a parabola. Specifically, a parabola from math class is something that changes as a quadratic in one direction, but doesn't in the other direction. It's a constant value. So, the other thing I want to talk about we're still doing here is speed. If this is moving at some speed, horizontally, it's always going to move at that same speed. But vertically, no motion. It's going just a little fast. It's going faster. It's going even faster. We calculate these separately, but we may want to put them together. If I grab another color, pink. Here the ball is moving perfectly horizontally, but 1 second later, it's moving at some angle below the horizontal. Later, it's moving at even a steeper angle, and even later, it's moving even a steeper angle. But it will never reach moving perfectly vertical, because it always has to move sideways. So now let's do a calculation. We're going to do an example problem. So here's a lovely cliff. It is 20 meters high, and we have a person, and he throws a ball nice and fast at 25 meters per second. That's about 60 miles per hour. You know it's going to arc down in a parabola. And the question is, how far away does it land? So hopefully everybody's pretty comfortable at this point about how far means displacement. There are two displacements in this problem. The horizontal displacement is what we don't know. We do, however, know the vertical displacement. I'm going to use x and y for horizontal and vertical, just like in math class. So if I go to this velocity, yes, this is the initial velocity, but it's only in the x direction. There is no motion in the y direction, so the initial vertical velocity is 0. So we're going to have two we're going to always have to work with both directions. So horizontally, we have constant velocity. And with constant velocity, there's only one equation. Velocity equals displacement over time, or rearranged, displacement is velocity times time. Now I wrote this as initial velocity in the x direction, and now I wrote final velocity in the x direction, but it's a constant velocity. So it doesn't matter which way I express it. Now I want to know x, the horizontal distance that it lands away. I know the horizontal velocity, but I don't know the time. Time is determined by the height, double exclamation point. So now we're going to go to vertically. We have acceleration due to gravity. So I am going to rewrite our acceleration equations. Instead of just v equals v naught plus at, vy equals v naught y plus ay t. The second equation, y equals voy t plus 1/2 ay t squared. And the third equation, vy squared equals voy squared plus 2 ay y. So on the College Board formula chart, the first three equations have all those little x subscripts. The purpose of that is to emphasize that you cannot mix directions. If you're talking about acceleration in a particular direction, you have to use initial and final velocity in that same direction. So on the formula chart, they're all x's. I wrote them all y's here because we're talking about the vertical direction, so the y direction. All of these ay's are, of course, gravity, 9.8 meters per second squared down. Yes, you will use the first and third equations. Not as often, though. We do not as often care how fast the object is moving in the vertical direction right before it lands at the end of the problem. We are usually more interested in the relationship here, time and height. So if we go back to this problem, if VOY is 0, this equation has a shorter version, y equals 1/2 ay t squared. And you know we can rearrange that easily. T equals multiply by 2, divide by ay. Don't forget to take the square root. So I can find the time to the ground for this problem. Square root of 2, the vertical displacement was 20, and the vertical acceleration due to gravity is 9.8, of course. Now you may be wondering, wait, 9.8 down, it should be negative. You get to pick the directions for negative and positive. Of course gravity's down, but the ball moves down 20 meters. So if I make down my positive direction, I can use 20 and 9.8 both positive. If I make this negative, 9.8, then I would have to also make this negative 20, which also makes sense mathematically, because if one is negative and one is positive, you have a negative under the square root, which is impossible. So we plug this in the calculator, and we get 2.02 seconds. Now we can finally go back to this equation and answer the original question. The horizontal displacement is the horizontal velocity times this time, and so this ball is going to land 50.5 meters away from the base of the cliff. So this is 50.5 meters. Now, I could give you the information in a different order. As long as I tell you it's launched horizontally, I could give you both displacements. You could use this one to find the time, and this with the time to find that initial launch velocity. I could give you the launch velocity and the distance away it lands horizontally. You could use that to find the time, and then figure out the height of the building. And on the problem set, I will ask you some information about the final velocity. Now, these are the vertical velocity components. If we go back to this picture, if this was the ground right here, and I asked you, how fast is it moving when it hits the ground? Well, this equation, or this one, depending on what I tell you, will give you the vertical component, what I drew in red. But I'm asking you for the total speed in pink. So you've got to include the blue horizontal velocity. So this is a resultant problem. You'd have to put together the two components to find the resultant. And yes, you will have to find the angle also, which you can see is pretty steep. Goes from little to bigger, getting closer and closer to vertical, but never quite reaching it.